So, in this session we are going to learn about the transistor, the working of a transistor as a device. So, how it can be used as different types of devices. So, we will see its role as an amplifier that can amplify this voltage signal, they can amplify current, they can amplify power as an amplifier. Next, as a switch we can see how it can be used to operate a switch. And third, as an oscillator. So, there are three device usage we will study for a transistor. Let us go back to the output characteristic in a common emitter configuration. So, in output characteristics we plot IC, that is in milliamps, and this is VCE, that is in volts. So, for different values of IB, suppose IB is 5 microamperes, for this I got 1 milliamps current. Then again we have IB is equal to 10 microamperes, for which nearly I got 2 milliamps current, and like this. So, we have a family of curves. So, now this region, there are three regions, this is region 1 and this region is 2, from here to here region 2 and this region 3. So, if an amplifier has to be used, if the transistor is to be used as an amplifier, we have to work in region 2, that is called active region. So, active region amplifier can be used, the transistor can be used as a device. So, let us denote this region 2 as active region. So, transistor can be used as an amplifier in this region. Now, as a switch, if we want to use, this region is called cutoff region, and this whole region is called saturation region. So, if the transistor is operated at this point and this point, these two are the operating points, then it can act as a switch. So, in this off position and when it is operated in on position. Regarding oscillator, we select the point something like this. That means it should be always in active region, and at one time it comes to saturation, then again to cut off. So, between here to here. Whereas in an amplifier you should not touch the boundary, you should be within this active region, and saturation means this region and only this region. So, this here oscillator can be used, and between these 2 points we have to use this switch, and amplifier can work in this region. Let us see with this circuit diagram in common emitter mode. Now consider the operation of a base biased transistor in common emitter configuration. This is important point, it is base biased and common emitter configuration. So, this is my transistor, this is the base, this is the emitter, and this is the collector. Now, here I have a resistor I call it RB, and here I am going to give the biasing this side. This is urged, and here again we have a R collector, then again here I have to give a biasing, and we are taking this V out here, and here we are going to V input here. Now let us bias it at these two places. So this is NPN type transistor. This should be forward biased. So N should be connected to the negative terminal, and this is connected to positive terminal. Here this junction should be reverse biased. So this N should be connected to this positive terminal, and here biasing should be more. And we see if I vary this biasing, so this is the variable voltage here. See the biasings and draw the diagram first. So now this is the input side and this is my output side. The input is taken across these 2 points and output is taken across these 2 points. Now let our diagram be somewhat clean. So now let us apply Kirchhoff's law, voltage law in this input circuit. Applying Kirchhoff's voltage law to the input circuit. So you see here this current flows through this is IB, and here the current is IE. So now let us plot V0 versus Vi. So here we are going to plot this Vi, V input along the x-axis and V output, how much output we will get. Let us write the two equations which we got. Input Kirchhoff's law in input circuit gives when Vi is equal to 0, then there is no IB, and so there is no IC. So there is no base current, so there is no collector current, and there is no collector current, so this is 0, so V input becomes VCC. That means here it is VCC. So my graph should come like this. So now with the transistor is in cutoff mode. We say the transistor is in cutoff mode. This is very important. This is the cutoff mode. Till Vi increases up to 0.6 volt for silicon or 0.3 volts for germanium, i.e. the junction, the emitter base junction becomes forward biased till that point the transistor is in cutoff mode. So what happens, as the voltage is increased, the base current increases, and so this increases, so Vi decreases. And you see a stage will come when my input voltage is the order of 0.6 for silicon, for germanium it will be 0.3. So this region will be called cutoff region. So once we reach this point, now if Vi is more than 0.6 volts, then the junctions, then emitter base junction becomes forward biased and collector base junction gets reverse biased. the transistor becomes active. That means transistor action begins to take place. The output voltage that is V naught decreases linearly with V input. So, you see we get a line like this. Till some points the order of this is nearly 1 volts. So, till this V naught becomes 1 volt, it decreases linearly and then it becomes here constant, very small and constant. When input becomes very large, when Vi increases to a large value where both the junctions are forward biased, then the transistor becomes saturated. So, this region is saturation region. We have cutoff region, this is active region, and this is saturation region. So, we have seen there are 3 regions. The output voltage is high at this place, the output voltage is low in the saturation region, and this is the active region where we have to use. This is the amplifier to be used in this region. When we have to use the transistor as a device, as a switch, then we have to work in these 2 regions. When we have to use it as an oscillator, so from this end to this end we have to use. This is how a transistor can be used as a device in the 3 regions. So, now let us see how a transistor can be used as a switch. Now, in digital applications, the transistor can be used as a switch. So, let us see how we can use as a switch. A small base current can be changed within a short time so as to change the collector current from a low value to a high value. That is from a on state to a off state. In a switch there are 2 states, switch on, switch off. So, when the transistor is in a on state, then the voltage at the load register is high, or the current is low, and when it is in off state, the voltage is low or the current is high. Current is high at the load register. So, this is what on and off state of a transistor means. The output is taken across the load register, that we will see with the diagram now. First take it. Now, you see here we are going to see how a transistor can be used as a switch. So, You see, this is my transistor and this is the common emitter configuration. This is emitter, this is base and this is collector. Here this is the collector biasing VCC and this is the load resistance RC, or the output is supposed taken across this emitter and collector. Let us see, whenever we are using a common emitter mode, the output is always taken across this C and E only. You may take output here, but generally trend is that majority of cases we take output here only. And this is the RB and you see this is VEB. So, in the input, this is a schematic diagram. The main diagram may be very somewhat complicated, other things will be there. So, in the input, we apply a voltage like this. So, the voltage will have some negative values and suddenly it becomes positive and then suppose it is negative. So, whenever, so this is some negative V1 I say and this is at V2. So, when I apply a negative voltage here, that means the voltage, this voltage at this level here and here, this system is reversed biased. That means this is reversed bias and the system is in cutoff mode. Cutoff mode means here we are in this region. So, suppose I do like this, this is cutoff region, this is cutoff region. So, suppose I am at this position. So, when the voltage, the signal V1 minus V1 is selected in such a way that this, whenever this voltage is this is in cutoff region. And when suddenly the signal changes from minus V1 to V2, that means this is in saturation region. That means my diodes, both the junctions will be forward biased and from cutoff mode to saturation mode we will shift, saturation mode. So, this region is saturation region. So, what happens when it is reversed biased? Then there is no conduction and there is very little IC, no current IC. So, there is no current ICC, so you will get maximum voltage VCC and IC is less. So, this region here, this region we say cutoff region. So, this denotes high voltage and low current. So, this state high voltage is called on state. And this state you see here, when this is under saturation region, then both these junctions will be forward biased. As a result, what will happen? Current will, IC will flow, voltage will be here less because current will flow here. So, there is potential drop here. So, voltage output will be low, which we have seen in this diagram. Earlier we have seen this is V input and the V output. So, initially this was here cutoff region and this was saturation region. So, in saturation region the voltage output is low. So, this here voltage is low and current is high. So, current is high and this becomes off state. So, this becomes on state and this becomes off state. So, the transistor here is given only two signals, only two voltages are given, V1 and V2. So, the negative voltage is selected in such a way that these junctions are reverse biased and transistor is in cutoff region and it is saturation region, it is in this off state. In this way the transistor acts as a switch. So, here one very important point. So, when we are using this switch, we want to know what type of switch. So, what type of signal we are talking about. You see, high voltage and low current for some applications may be considered as on position when my input is the voltage. When we concentrate on voltage, then high voltage for digital circuits, when high voltage is considered, when we are measuring voltages, then we take on position. But some applications, they concentrate on current, where current is important, where it is in conducting stage. So, in that case, that low current means non-conducting, and so this will become off and this will become on. So, depending on, we are taking the output as my voltage or current, we can define on and off in a different manner. So, if I talk about high voltage as on and low voltage and off, this is on and off. And when I talk that if low current is on off position and high current is on, so this will be accordingly off and on. So, off and on will depend on whether we are taking the signal as the voltage or the current. Anyway, we can take it. In the previous discussions, we studied the static characteristics, that is DC characteristics of the transistor. That means the input was a DC voltage. So, in amplification process, we are giving an AC input in the input circuit. So, we have to study the AC characteristics. Now, a small AC input signal is given in the emitter base side. So, a small AC input means how much small? So, the input signal that is AC is given along with a DC input, that is the bias voltage, so as to keep the transistor in active mode. So, the input signal AC, suppose this is the AC input signal, this is AC input. So, what we do we mix this with a DC input, so that my signal should be something like this. So that this and this, so this should not, this region, that means the current, this should not make it reverse bias and it should not come in saturation mode. So, we should keep in mind that the operating point, that means the signal given should be such that when connected properly with a DC bias, the whole signal makes the transistor to work in active mode. Let us see how we can do this. So, now let us see the working of a transistor as an amplifier. So, in the previous cases we have seen that we apply this, previous cases we just apply the DC here input, but here in an amplifier my input signal may be alternating, and so you see along with a DC bias there is an alternating bias signal. This is the signal and this is the bias. You see, this is must, because this will ensure that this plus this will give us always, this will make us this transistor to act always within the active region. So, let us see how this transistor is going to amplify. You see, the output is taken across this output. Output is generally taken across, this is the collector and this is emitter. Across collector emitter output is taken. So, let us first see that if there is no signal, alternating signal given, that means this is 0, that means here there is the current IC is due to this DC voltage. So, let us see that how much is how amplification will take place. Now, you see, I draw here, this is the output characteristics, and you see this is the graph. Suppose along this I plot T, and my current, you see, this is the current, suppose this is 15 microampere current, and here I will plot how this current varies. So, how the current this will vary, that is my IC will vary. This is, I am plotting T versus IC. IC is in milliamperes, this is IC, that graph. Now, you see here, if there is no input signal given, then the output DC, then the DC which we are giving here, that DC voltage gives a corresponding current equal to 15 microamperes. That means corresponding to 15 microamperes, we will have an IC value this much. So, this is the IC value we are getting corresponding to this. Now, when we give an input signal, when the input signal varies, then here this input signal will vary like this. So, this is our input signal. I am plotting input signal, I input, I in, I suppose I input, I am plotting it. So, input signal is suppose changing 5, so it changes 15 microampere current to 20 and 15 minus to 10. So, according to this, the current here, this current will also vary and this current will also vary. This is the current here that corresponds to that IC, suppose IC, and that will vary with this. So, you see this value is something I in. So, it is beta time I small I, and this is again beta time I. So, I mean I max. So, simply I will write this as beta I. Beta is the current amplification, that is beta here is beta, let us write beta as I collector by I base IB here. So, this is DC and this is AC, means beta AC and beta DC. So, you see here the current when there is no input signal is 15 milliampere, for which we have a value this current, and when this current increases, when the signal is given, then it gives up to 15 to 20 and from 15 to 10 microamperes. So, whatever the current here is there, this is plotted here, whatever the current here is plotted, this may be something, suppose this is here 10, so here suppose it is 2 milliamperes, this is 3 milliamperes and this is 4 milliamperes. So, from 4 milliamperes to 2 milliamperes, the current comes in the output circuit. In this way, amplification is done. So when there is no input signal, then we have some base current say IB. So, this is the operating point, we say that this is the operating point. So, the current say IB. So, this IB is here, and corresponding to which the collector current is IC, which is beta times IB. So, this is beta times IB, where beta is the current amplification, IC is beta IB. Now, when the input signal, then the input signal, that is AC signal, is applied, then the base current varies as you see, this is the variation of the base current. Let us call this IB, base current. So, applied to the base current varies as that IB is equal to this capital IB, this is, you see, variable, plus IB naught some sin omega t. That means this AC is added on this DC current. So, this collector current is due to this DC base current. Thus, we have a amplified current in the collector region as IC is equal to beta times IB plus IB naught some sin omega t. So, thus here we get an amplified current in this output circuit. This is how amplification is done. Here we should keep in mind that the DC voltage here we have applied. If we do not apply, then this may come in this region and this may come out of this region. So, we should keep in mind that we should apply the signal such that the current variation is from here to here, that means it should be always in the active region. If it comes in this region or that region, then amplification will not take place. Now, let us see the working of a transistor as an amplifier mathematically. So, this is the circuit transistor. The input is given an alternating signal along with a DC bias VVB, and here the output is taken across this collector and emitter. Here VCC is this constant bias and this is the RC register. So, the output is generally taken across the emitter and collector. So, now you see here, let us apply Kirchhoff's law in the input circuit. So, here input what we are giving is, suppose the sum of this. So, input Vi input, or suppose there is no input, this is 0. So, when it is 0 we say VBB. If this is 0, then VBB is equal to this IBRB, this is equal to IBRB plus this VBE. Now, this is if there is a change in this, you see this is constant, and if VBB is changed, so when we apply a alternating signal, we are changing this voltage. So, delta VBB is equal to delta IB, and this is RB plus this is 0. So, this is V input. What input is given, that will be the change taking place, that will be delta IB by RB. This is equation number 1. So, this is the input, Kirchhoff's voltage law to the input circuit. We have applied this to the input circuit. Now, similarly applying Kirchhoff's voltage law to the output circuit. So you see, this is the output circuit, the potential drop is here taking place like this. So V naught, we can write V naught as VCC minus ICRC. Now if there is a change in IC, that is, let us write this as not V naught, VCE. So a change in VCE will be, this is constant 0 minus RC is here delta IC. So the change in the collector emitter voltage, whatever, if any change is given, that change will appear this way. So how change will appear? This is called V output, that is minus RC by delta IC. Beta AC as delta IC by delta I base current. So you see, this is simply beta times delta IB. Now from 1 and 2, we get V naught by V input. V naught, that is V output by input, is equal to minus RC beta delta I beta upon V input, that is RB times delta IB. This cancels out. So we have V naught by V input as minus RC times beta by R base. So now we define voltage amplification as beta voltage is equal to V output by V input, that is minus RC by RB into beta times. The negative sign indicates that the voltage waveform in the output is lagging the input by pi by 2. So one more thing, if in some cases we take output across RC, then that voltage output won't be lagging, they will be in phase. But since in majority of the cases the voltage is taken across the emitter collector junction, so the voltage is lagging this input voltage by pi by 2. Next, power amplification, P will be PAC will be equal to voltage into current amplification, that is beta AC into this, that is beta voltage amplification. We generally denote not by beta but A. The letter for this is A. So let us write this as A voltage, AV. So now let us see how the transistor can work as an oscillator. So an oscillator is also an amplifier. So in an amplifier an external AC input is given, which appears as amplified output, amplified AC output. So, thus we require an external AC input. So, this is the requirement for a amplifier. In an oscillator, the input is taken from a portion of the output in phase. Thus an oscillator is a self-sustained amplifier. So, no AC input is given, the input is taken from a portion of the output itself. The process of extracting a input from the output is through a feedback system. If the signal extracted is in phase with the output, then it is called positive feedback. So, what we have discussed now is an oscillator is also an amplifier in which there is no need of external alternating input. A portion of the output is fed into the input. So, it is a self-sustained amplifier. Now, let us see how it works. In an oscillator, there are three main types, ingredients. We say this is tank circuit. So, through a tank circuit, we have taken an input. We take a input, from a tank circuit. This is called a feedback system. So, this is a feedback system. So, and there is an amplifier. This is an amplifier or simply a amplifier or a transistor, we can say. This is our feedback system. Now, this tank circuit is connected to an amplifier, and this amplifier through a feedback system is connected. So, this is the block representation. So, there are three important elements. One is the tank circuit, another is the amplifier, which is actually a transistor with its biasing and all those things, and this is a feedback system. So, inside this there is an inductor L and there is a capacitor C. So, this is an tank system, this is the oscillatory system. So, in this system electrical oscillations are sustained and produced with a frequency of f is equal to 1 by 2 pi root over LC. This is the frequency of oscillation sustained in this tank circuit, L and C in parallel. Now, this is connected to the amplifier by a feedback system. This feedback system can be of RC type transformer, that is based on mutual inductance, that is transformer. So, through a transformer we will see this. So, there are different types of feedback systems. Accordingly, the name of the oscillators are given. The name of the oscillator is based on the feedback system. Feedback system can be positive system, can be negative system. When this is in phase, so when this transistor is used, the input given is in phase with the output, then we said it is a positive feedback. If it is out of phase, then it will be a negative feedback. And then this transistor amplifies this signal and sends back. So, whatever the loss is taking place at L and C, that loss is compensated by the transistor. In this way, the transistor acts as an oscillator. So, now in an oscillatory circuit, LC oscillation, the time is here plotted, and suppose this I plot I, then oscillatory circuit, the current varies like this. This is the oscillatory current we expect in, this is I max and this is I min. But actually, due to some resistance of the coil, the current varies like this. The current varies and it gets damped like this. So, that will become a damped oscillation. Damped oscillation. So, what we have to do? So, you see this is the constant value. So, we have to pull these portions here, and so what is required is this, and due to this damping, this loss of energy, the oscillations goes like this. So, this is a damped oscillation. So, the role of amplifier, the role of transistor is to feed this system this energy. So, whatever the loss of energy is that, and so to make this damped oscillation to like this. So, what we do, this is the maximum current and this is the minimum current. So, what we do, you just recall the output characteristics of an amplifier. This is VCE plotted here, and this is the collector current. So, you see this is the IB current, base current, and so we have this region like this. So, this is the saturation region and this is the cutoff region and this is the active region. So, suppose here this minimum current is and this is the maximum, my current should vary, oscillate along I max and I min. So, we select VC in such a way that you see the current varies like this and goes like this. So, you see when you are at this maximum, this is I max and this is I min. So, when you are at the minimum position, then it gets cut off, and you see we adjust our settings, we will see it with the circuit diagram. So, when the current is minimum, this is coming into cutoff region, and when the current becomes maximum, it is becoming saturation medium, saturation mode. And throughout maximum and minimum, whenever a current is between maximum and minimum, then the amplifier is in active region. So, you see here these are the operating points, that is we should take care while we design the circuit for an oscillator, that the minimum current should be here and maximum. So, when maximum current is there, it is in saturation, when minimum current is there, it is in cutoff mode. Let us see how we can do so. Now, let us see the connections. This is my transistor with this as base, this as collector, and this as emitter. This is emitter. So, here the collector is connected to a LC circuit. Here this is my tank circuit. Here I am going to put my tank circuit here, and then you see. So, in a tank circuit we will give here an inductor. So, this is an inductor, that is L, and this side we will put this capacitor. So, this is my capacitor. Here I will apply my biasing voltage with a switch also. So, this is a switch here, switch and biasing voltage. So, this is NPN type N. So, N is, it should be forward biased. So, you see here we will give up a, this is NPN type, NPN type. So, this N means forward bias, means it should be connected to positive terminal, and here also we have to give bias positive negative, here the bias should be more. So, let us now to this inductor coil is connected on the primary of a transformer, primary. So, this is the core, and here we have connected it to an output. So, this is output, the output is connected on the secondary. Now, on the secondary we have one more coil connected here, that goes to here, and you see here this coil here we can, this is connected here to the collector, and there is this coil is one end connected to the base. Here I have given it to the base, and then this is connected back to the cell. This is your emitter, and so let us see this biasing is some, here biasing is wrong, this is now forward biased, and this is, so this is the biasing. So, this is N type, so it should be connected to N, so forward biasing. Now, here you see this is the core, and we have connected a coil like this. So, now what happens, you see here this LC oscillation is there, and this is connected to the collector, and this is my transformer. This is the feedback system. So, whatever current varies in this LC oscillation, it fluctuates like this, goes on. So, that will be induced here, and that is again feed back into this emitter base side. So, you just recall this is the base, I have not shown some resistors etc. So, this is the base and this is the emitter. So, input is given in this and output is again going back into system. One more important point, here whatever loss is there, that is compensated by the work done by the cells. So, the power loss is compensated by the cells, that is DC cells. So, now let us see the working. So, when you switch on the key, what happens? The current here voltage begins, and you see this is the inductor, it provides inertia to the flow of current. Previously there was no current, so current increases slowly. So, suppose here the current, I plot current, time and current, this is I, this is IC. So, this is IC. So, IC, and let us plot IB. So, what happens? When we switch on the key, the current grows slowly, the current grows slowly and until it reaches maximum. So, when the current grows, grows slowly, the magnetic flux grows on, and so there is a current induced here. So, this current, base current also increases in a similar manner. What happens? Here the current, here when the voltage increases so large, that here the system comes into saturation and both these junctions get forward biased. So, here saturation is there, saturation, and then the current begins to decay, and so it decays like this, and so is the current IB also. Next, so the moment it comes here, then it gets into cutoff mode. So, when the current in this inductor becomes 0, when this current is in the inductor is 0, that means this is fully charged, and so the voltage here is minimum, this minus this voltage. So, the voltage this and this is so adjusted that when this is peak voltage and this minus this is the cutoff voltage, that means at that time this will become reverse biased, both junctions will get reversed biased. So, the voltage here and here it adjusted in this manner. So, again, so when this becomes 0 cutoff, then again the current begins to grow up, and so this will also grow like this. So, important point as at these positions the transistor comes in saturation region and these regions cutoff regions. You see the current oscillates over this. So, the current is made constant this with the help of this. So, very important point is to understand that when the transistor is used as an oscillator, the transistor should be in active region and just touching at these maximum and minimum points, saturation and cutoff. This is how a transistor can be act as a oscillator, that is a self-sustained amplifier.